Good morning, sir.
Good morning, Brendan. And hello, everybody. How are you today?
Good. How are you?
Okay, thank you. Okay, well, welcome back, everyone. Hope you had a nice weekend. We're going to start ramping up our pace in the course, really getting into content. And I hope you and your families continue to remain healthy. So some exciting news, right? You have most likely heard that next week, starting next Monday, we are going back to school. Hooray! We're going back to school starting next Monday. Okay, so next Monday, the 31st, classes are back in session. So next Tuesday, we'll be together on campus. Okay, we'll be together on campus. And as you know from your syllabus, the room we will be in for lecture is East 227. East 227. Okay. So let's see, next Tuesday is February 1st. And so please drive to campus next Tuesday and we'll get to see each other in person, okay? Do you have any questions about that process that's going to unfold next Tuesday? Okay, well, please let me know if you do. Cassandra has a question about parking passes. Cassandra, as far as I've been told right now, as long as you have your state issued driver's license with you, you're not going to be hassled about parking right now because we're just getting things situated. Okay, so I don't think you need to worry about parking passes at the moment. Okay, anything else? So obviously when we get back on campus, things will be a little bit disheveled, right? I mean, we haven't really had classes on campus for nearly 2 full years. So I expect there's to be some rough patches, but it will be exciting to be back, okay? So just remember your mask. We all need to wear masks while we're on campus, but hopefully we can return to some sense of normality next week. Okay. Okay, Brendan, please go ahead and ask your question.
When I was working on the homework assignments, many times I seem to have lost connection and had to reconnect to work on them again. And it was pretty consistent, like every 2 to 3 questions on the part 2 stuff.
Okay.
So I just wanted to ask that to see, like Ray, that I wasn't the only one.
Okay, yeah. So if multiple people have been experiencing some kind of connectivity issue, obviously you're not insane. From time to time, Wiley Plus, being a computer-based service, does have some computer issues, some technical issues, and so that can happen, unfortunately. I know it's frustrating, it's aggravating in the moment, but usually it does resolve itself. So I would say, unless this continues to be an issue, just wrestle through it in those occasional moments. Typically, if there's a major disruption in the service, I will get an email from Wiley Plus letting me know that there's been an issue. As far as I can remember looking at my email, I did not get such an alert. So, I'm sorry that happened, but please continue to let me know if it does get worse and more people are experiencing it. Then I will reach out to our representatives at Wiley and see what the heck's going on. So, okay. Okay, anything else? All right, let's continue. We're going to wrap up chapter 1 in maybe about 30 minutes here, and we'll be on to chapter 2, okay? So I'm going to share my screen with you. And what I've done is copy some of the notes we took from last time. So remember, last time we were talking about feedback systems, and we were describing the components of the feedback system. So far, we have described receptors, which are the body structures that monitor a condition, such as blood pressure or blood glucose, or in the case of, we were talking about taste buds being receptors, so the taste buds would monitor the conditions in the mouth in terms of what molecules are present or absent, okay? So we started with receptor. We went on to define the control center. This is a body structure. It is often the brain, but not always the brain, that receives information from the receptor and processes that information to determine if the condition being monitored is normal, is healthy, is homeostatically correct, okay? And so let's continue with using so we start with the taste buds. So let's say that you put something in your mouth that's overly bitter or overly sour or overly sweet. I mean, just intensely so. So the taste buds are going to detect that. They're going to send information up to the control center, which in this case is going to be the brain. There's actually a region in the right hemisphere of the brain called the gustatory cortex. That's going to contain the neurons that actually receive that information and process what the heck's going on with your taste buds, okay? So the control center example in this case would be brain. And as I said, specifically, the gustatory cortex. If you're very curious during your private study time, you can find the gustatory cortex on figure 14.15. 14.15, you can find it there. Okay, we will be talking about some topics in chapter 14 towards the end of the semester. All right, but right now we're talking about the anatomy of a typical feedback system. In our example that we're walking through, you put something overly sour in your mouth, your taste buds detect that, they send that information up to the brain, which is going to act as the control center. The brain's going to determine whether that is good or bad, whether it's healthy or not, whether it's homeostatically proper or not, okay? And then the control center, in this case, the brain is going to elicit some kind of instructions to an effector to potentially respond to that abnormality in homeostasis. So in the case of putting something overly sour or bitter or sweet in your mouth, you know, you might have had the experience in life where you've done something like that and you kind of pucker your mouth up or even spit the material out, right? Because it's really unpleasant and you just don't want that sensation anymore. So the response in this case could be to coordinate contraction of your facial muscles, to pucker your lips, or to actually spit the content out of your mouth, okay? So the third element of a feedback system would be what's called an effector. All right, so let's define that. An effector refers to a body structure that receives information from the control center and potentially takes corrective action based on the information it is receiving from the control center. So once again, an effector refers to a body structure that receives information from the control center and which may take corrective action to restore homeostasis based on the instructions received from the control center. Okay. So sticking with our example at this time, you've put something uncomfortably sour or bitter in your mouth. The receptors of the taste buds detected that, sent electrical signal information up into the brain, into a subregion of the brain known as the gustatory cortex. The cells are looking at that information from the receptors and saying, hey, this is too sweet. I don't like this. This is too sour. This is too bitter. I don't like this. So this is not healthy or helpful to me as an animal. So the gustatory center of the brain is going to send new electrical signals back down the neck and in the mouth, and it's going to tell the facial muscles to pucker and spit that content out of the mouth. So in this case, the effector would be facial muscles. Okay. All right. Okay, folks. So let's see here. Let me see if I can give you some more examples. Let me see if I can give you some more examples here. Okay, so any questions about the definitions of the components of the feedback system, effector, control center, or receptors? Okay, receptors, control centers, and effectors. Any questions at this time? Okay, let's make a table here. Let's make a table here, and we'll give some more examples of things that we could define as receptors. More examples of things that we could define as a control center. More examples of things we could define as effectors. Okay. So examples of receptors, control centers, and effectors. Okay. And what I'll do is place this into hopefully a fairly organized table at this time. Let's see here. So we're going to have about 5 rows and 4 columns worth of content here. Okay, so in the first column, I will indicate the condition being monitored. I will indicate the receptor in the second column. I will indicate the control center in the third column and indicate the effector in the fourth column. So let me make the language of the first column a little shorter. The monitored condition. Okay. So let's say the monitored condition is going to be blood sugar. Okay, it's going to be blood sugar. Okay, and so let's say the condition where we have some kind of stimulus, such as you ate some candy, so your blood sugar gets high. Okay, in this case, the receptor is going to be the pancreas. Okay, one of the receptors is going to be the pancreas. So the pancreas organ is made of tissues, which is made of cells that have the ability to detect and monitor the blood sugar. Okay. The control center in this case is going to be the subset of cells in the pancreas that actually have the ability to measure that blood sugar and make a decision about whether it's homeostatically normal or not. So in this case, the control center are going to be the beta cells of the pancreas. And the effector is going to be the cells that respond to instructions released from the pancreas. Okay, so now in our first example here, where we were talking about, the taste buds and the brain and the facial muscles, okay, in this example, communication was always electrical because the taste buds sent electrical information to the brain processed it, sent electrical information back to the facial muscles. But in our first example of this table, when the beta cells of the pancreas decide that, oh, blood sugar is too high, it's not going to send electrical signals per se. It's going to send a different kind of control signal, which is a hormone. In this case, insulin, right? Insulin is going to be released into the bloodstream, and insulin is going to bind to cells that have the ability to lower the blood sugar. So in this case, the effector are going to be both the liver and skeletal muscle cells. Okay. All right, so once again, we're monitoring blood sugar. Let's say something has caused it to become high. The pancreas is the organ that detects that. That's the receptor. The control center is the cluster of cells in the pancreas that we call the beta cells. They monitor and measure that blood sugar. And then they say, oh, well, blood sugar is too high, so I need the body to return to homeostasis. And the only way that's going to happen is if I lower blood sugar. So the beta cells will release the insulin, and then the liver and skeletal muscle cells respond to the insulin and cause the glucose in the blood plasma to enter the liver and skeletal muscle cells. That lowers the blood sugar, and we restore homeostasis. Okay. So question in the chat window here. Am I making sense right now? Does this logic work for you? Can you understand what's being communicated? Okay, would you like to ask any questions? All right, sounds like we're doing okay, and that's fantastic. Let's do a couple more of these things. Let's say we have blood sugar being monitored. But in this case, we're going to talk about, well, what if blood sugar is too low? What if blood sugar is too low, right? Because sometimes it's not too high, sometimes it's too low. Well, once again, the receptor is going to be the pancreas, because the pancreas is the primary organ that deals with regulation of the blood sugar. So the pancreas organ is the receptor. Okay, obviously it's made of tissues, which are made of cells. And there are different cells that are going to deal with the condition of low blood sugar. The control center in this case would be a different subset of cells in the pancreas called alpha cells. The alpha cells of the pancreas, let me ask you a question in the chat window. So you are all familiar, I think you're familiar that when blood sugar is too high, the pancreas responds by releasing insulin. But let me type this into the chat window. Here we go. What is the name of the hormone released from the pancreas when blood sugar is too low? Have you come across this one? Because the pancreas is going to release a different hormone than insulin. When blood sugar is too low, what's the name of the hormone the pancreas will release? Okay, so I'm going to run with Brendan's comment. Brendan, you are correct. You misspelled it. That's okay, but you're correct. It's glucagon, glucagon, right? So the alpha cells of the pancreas will release glucagon. I'll put that in the chat window. Glucagon will be released, and that will float in the bloodstream, and it will cause the liver and skeletal muscle cells to respond not by taking up glucose, but by releasing glucose that has been stored inside the cells and pushing it back out into the bloodstream. Okay. So, at this point of the course, I certainly don't expect you to be an expert on the endocrine system or anything like that. I don't expect that you would know about beta and alpha cells or anything like that. But I think you can appreciate from, most people have been around long enough. They know people with diabetes. It's part of our common societal conversation. People kind of know about insulin and sugar and diabetes, hopefully the pancreas as well. So hopefully this is making some sense here, okay? Any questions? Okay, so I'm going to do one more with you, actually. And that last row I ended up not needing. So let's talk about let's talk about a monitored condition being blood pressure. Okay, blood pressure. So let's talk about the scenario where blood pressure is too high. Okay, something has happened to cause the blood pressure to be too high. Maybe it's because you're scared. Maybe you're experiencing some kind of traumatic, scary situation and your blood pressure is shot up. Okay. So in this case, the receptor is going to be what are called baroreceptors in blood vessels. Okay. So in the walls of your blood vessels, okay, so the wall of the blood vessel is made of multiple layers of tissue, which themselves are made of multiple cells, right? So the walls of the blood vessels will have molecules that change their shape in responses to changes in pressure. And these molecules are generally called baroreceptors. So literally in the fabric of the anatomy of the blood vessel wall, you have molecules that change their shape in response to changes in blood pressure. So if the blood pressure is too high, these baroreceptors are going to detect that. And they're always connected by neurons to the central nervous system, right? So the receptors will activate an electrical signal that goes up to the control center, which in this case is the brain. Okay. The brain is going to process that information and say, oh, we have a problem with blood pressure right now. It's too high. So we're going to have to lower the blood pressure. Okay. So the brain can do this a number of ways. And there can be a multitude of effectors that help coordinate a response to lower blood pressure. But I'll simply mention right now that probably the most logical thing you would think of is that if the blood pressure is too high, the blood vessels have detected that. They've communicated that information to the brain. The brain says, oh, yeah, we do have a problem. We need to respond. We need to take corrective action to restore homeostasis. Then the brain will send electrical signals down the heart, down to the heart, and tell the heart to slow down, to slow its contraction rate. And by slowing contraction rate down, you can adjust your blood pressure. You will learn really at the end of our semester together that one of the primary regulating nerves that leaves the brain and goes into the heart is the vagus nerve, okay? So in this case of our overly simplified scenario right now, the brain will communicate to the heart, and then the heart will slow its slow its contraction, and you will start to moderate blood pressure. Okay. There's other things that will regulate blood pressure as well. It's not quite as simplistic as I'm suggesting in the table, but right now we're trying to understand the basic ideas of feedback systems, what a receptor is, what a control center is, what an effector is. Okay. All right. Any questions? All right. So this is a really, the idea of feedback systems and how they monitor and respond to changes in homeostasis is really deeply important for our course. You're going to be encountering many scenarios throughout not only AMP1, but AMP2 as well, where you need to think about feedback systems, receptors, control centers, effectors. And so it's worth the effort to really be sure you get this idea firmly situated in your mind. And so we're going to do one more thing here where I present some information to you as a group, and then I'm going to go around the room, the virtual room here, and ask each of you a question to be sure that we are in fact understanding this content. Okay, so let's do let's do a question and answering session on a hypothetical feedback system scenario, okay? All right, so I'm gonna bump to a brand new page in my notes. A hypothetical scenario using feedback system logic, okay? All right. So I'm going to define a silly little scenario, which, could really happen in real life, but, this is just a little way to start thinking about this. And then I'm going to start posing some questions to those of you online with me here today, okay? So let's see what we can do. All right, so here's the scenario. Let's say that you are inside your house on a winter day. Well, lo and behold, we're inside our house on a winter day, aren't we? All right. Number two, you're looking out the window and you notice the mailman has in fact delivered your mail. So you decide to go get your mail, which means you walk outside without a jacket on to get your mail. Okay, I'm sure all of us have walked outside to do something very briefly, such as get your mail, and everything normally goes just okay 99.9% of the time, right? But what happens if you accidentally lock yourself out? Then you got trouble, don't you? Well, okay, let's continue here. Okay, so you go outside to get your mail. While you're walking outside, you're going to have nerve endings embedded in your skins. They're going to be both in the epidermis and the dermis, but we'll just say skin for right now. So nerve endings embedded in your skin detect a change in body temperature. Number four, okay, those nerve endings report a change in body temperature to your brain. Your brain decides that there is an issue with body temperature, that homeostasis has been altered. The The brain decides that body temperature, I'll say it this way, the brain decides that body temperature is no longer homeostatically healthy. The brain then communicates to the skeletal muscles along your entire skeleton to begin repetitive cycles of contraction and relaxation, which we know as shivering, okay? All right, so with this kind of silly little scenario, which is still nonetheless realistic because we've all been outside on a cold day and we've all started to shiver, haven't we? Okay, so let's ask some questions here. Okay, so question 1. Okay, so I'm literally going to give everybody online with me a question. So don't be shy. Okay, don't be shy. All right. So I'm just going to take the list as I have it here. So Asasia, could you unmute your microphone and say hi to us, please?
Hello.
Good morning, Asasia. How are you?
Good. How are you?
I'm okay, thanks. So Asasia, my question to you is, in our silly little scenario that I just typed into the computer, what body condition is being monitored?
Body temperature.
Okay, yes, I had to focus to be sure I heard you, but you're absolutely right. It's your body temperature. That's the condition being monitored. Good job. Thank you. Okay, so you can see, folks, this is fairly easy stuff, although some of the questions might start to get a little bit more meaty. Okay. Jared Schaefer. Jared, please say hi to us.
Hi, good morning.
Good morning. Jared, what is the stimulus that caused a change in body temperature?
The stimulus is the low temperature outside affecting the nerve endings in the skin.
Okay, so what is the thing in the environment that has low temperature? It is the
air.
The cold air. There you go. So the stimulus is the cold air, right? Okay, good job. Okay, let's continue here. Brendan, please say hi to us.
Hello.
Good morning, Brendan. Hey, Brendan, what is the receptor in this example? What is the receptor? If we're thinking about feedback system component terminology, what is the receptor?
I believe the receptor would be the nerves in the skin cells that are receiving the information about the cold air.
Beautifully done,
detecting it.
Brendan. Beautifully done. Good job. Nerve endings in the skin are absolutely the receptor here. Okay, let's continue. Okay, let's see. Jack Kiefer. Good morning, Jack. Please say hi to us.
Good morning.
Good morning, Jack. Jack, in our example, what is the control center?
I'm gonna say the brain.
You are absolutely right, Jack. I mean, I would say about 7 times out of 10, if you have to guess brain for control center, you're likely going to be correct. Okay, so good job. And the point of it is you don't have to guess here, right? Because the information in the scenario does tell us that nerve endings communicate to your brain. Your brain is, in this case, going to be the control center. So the brain. All right, next question coming up. Okay, so Cassandra. Please say hi to us.
Good morning.
Good morning, Cassandra. Cassandra, my question to you is going to refer to something that we covered at the end of last class. Cassandra, when the nerve endings in your skin send information to the brain, did the nerve endings use afferent or efferent communication?
Oh, they'd be going away, correct? Afferent.
Yes, absolutely. You're exactly correct. Okay, so I'll highlight this in our notes again up here, right? From receptor to command center is afferent communication. And when we have communication from the control center to the effector, that's efferent communication. Absolutely. Nicely done. Okay, so the question was, what form of communication took place between the receptor and control center? And it was afferent communication. Question 6. Okay, question 6. Let's see here. Okay, Ray Ober. Good morning, Ray. Please say hi to us.
Hello.
Hi, Ray. Ray, your question is, in our example right now, what is the effector?
The skeletal muscles.
Nicely done, Ray. Perfectly reasonable. The skeletal muscles are the effectors. Absolutely. Okay. Good job. Okay. Next question. And forgive me as I look back and forth between my attendance list and my notes here. Okay, Alana Sterner. Alana, please say hi to us.
Hello.
Hi, Alana. Alana, your question is this. In our example, why did the skeletal muscles begin shivering?
To warm up the body temperature.
Okay, that is a true statement. And what was it that ordered the skeletal muscles to do that?
Like the brain trying to maintain homeostasis.
Good job. That's what I'm fishing for. Nicely done. You're absolutely right. Why did the skeletal muscles begin shivering? And the answer is the brain, the control center, determined body temperature was abnormal and ordered the muscles to shiver. Okay. All right. Good job. Question 8. Okay. Let's see here. Lauren Umble. Lauren, please say hi to us.
Hello.
Hi, Lauren. Lauren, your question is this. When the brain communicated to the muscles to shiver, did the brain use afferent or efferent communication?
Is it efferent?
It is efferent. Absolutely right. Good job. So I'm just going to complete the documentation in your notes. Okay, question 9. All right. Question 9 goes to Brittany McKinney. Good morning, Brittany.
Good morning.
Hi, Brittany. So Brittany, you just happen to be the lucky person that's going to get what might be the hardest question here, okay? So don't let it scare you, but I want you to think about this, and it's going to be a question that we haven't explicitly defined in our notes yet. So here's my question to you. The example that we're talking about, You're inside your house, you go outside, your skin detects a change in body temperature, reports it to the brain says, hey, we're out of homeostasis, we need to take corrective action. So the brain orders the skeletal muscle to shiver. So Brittany, your question is this example we're talking about a case of positive or negative feedback?
Negative?
Okay, Brittany, you said negative and you are correct. Can you tell me why that is correct?
I couldn't tell you, I just guessed.
Okay, I appreciate the honesty there. Let's open that question of explaining why to anybody in the room. Anybody want to take a shot at that? Brendan, go ahead.
I'm not sure I've got this either, but I want to take my shot at it. Is it negative because it's something being removed from the situation? In this case, you're losing heat.
Well, Brendan, you're on the right track. I would need a little bit of a different way of communicating that to complete the circuit, so to speak, but you're not wrong in the information you're sharing. You are on the right path. Can anybody help Brendan bring this full circle? Anybody? Okay, to move things along, I'll define it for you, okay? This scenario we're talking about, the response is negative because we are trying to warm the body up when it is too cold. Okay, now I'll define this in your notes and then we'll spend some more time thinking about this. So in this scenario, the response is negative because the skeletal muscles are attempting to generate heat to warm our body. Okay, so think of it this way. Negative feedback happens anytime the response of the body is to counteract or reverse the consequences of the stimulus. What was the stimulus? The cold air. The cold air made us cold. We don't want to be cold, we want to be warm. So negative feedback is anytime when the body reverses the effects of the stimulus. Okay, negative feedback takes place anytime the body works to reverse the effects of the stimulus. Okay, positive feedback takes place anytime the body works to amplify or enhance the effects of the stimulus. Okay. All right. So with these definitions, okay, of negative and positive feedback, what I'm going to do, I hope, is ask another question or two. Okay. So, all right. So, Julian, could you please say hi to us?
Hi.
Hi, Julian. Julian, do the definitions of negative and positive feedback make some sense to you?
Yeah.
Okay, so let's let's ask a question to tickle you on this a little bit. So Julian, here's my question to you. If you are the person that's outside and your body temperature is dropping, and for some silly kind of stupid reason, you wanted to do something to intentionally create positive feedback in this scenario, what could you do?
You can make yourself like warmer by like wearing a jacket or even like running or something just to cause your body to heat up.
Okay, so thanks, Julian. I appreciate that. Now I'm
Yeah.
going to ask a question in the chat window. Hold on a second. Do you agree with Julian's answer of wearing a jacket as positive feedback? Do you agree with him? Okay, so I want you to respond. I want you to think. I want you to respond. And then I want you to look at your classmates' responses in the chat window and see, if there is a consensus on this. Okay, so Julian, as you look across there, you can see that we have some yeses and we have some nos. So there is definitely not a consensus here. And so Julian, Julian, I would say that I disagree with your response. Okay, I disagree with your response. So let me ask Naomi Mars. Naomi, can you say hi to us?
Hi.
Hi, Naomi. Naomi, do you agree or disagree with Julian on this question?
I would say I disagree.
Okay, so could you give me an example of something silly you could do to create positive feedback in our situation?
Well, if it's positive, wouldn't you want to enhance what's happening to you? So you'd want to be more cold?
That is correct, Naomi. Beautifully stated. You want to get more cold because this is positive feedback. You want to enhance the stimulus of the cold air. So, Naomi, what could you do?
I don't know, like take your shirt off.
Okay, that's a nice answer. That's right. You could take your shirt off. If it's a winter day, maybe there's a pile of snow on the side of your driveway. Maybe you could jump in the snow. I mean, it's silly, but that's the point. What could you intentionally do to create positive feedback in this scenario? Okay, so good job, Naomi. So Julian, let me come back to you one time. So Julian, let me change the scenario. Julian, let's say that you're out walking with your son or daughter and it's trick or treat, it's Halloween. And their blood sugar is going up a little bit because they've had a piece of candy, Julian. As a parent, what could you do to create positive feedback in your child's blood sugar?
Like if it's going up, just give them more candy.
Okay, that's what I was fishing for, Julian. Good job. That's exactly right. That's exactly right. Okay, folks. So hopefully you can see that these concepts are very understandable. Receptor, control center, effector. The only nuance is understanding what negative and positive feedback really is. And I would caution you that when you talk about negative feedback, you do not want to interpret that from an emotional, psychological perspective. Because we think, in the example of being outside and being cold, we think of being cold as being uncomfortable. And so that's psychologically a negative kind of thing. We don't want to be uncomfortable. So if we put on, if we put on a jacket, that provides a positive response because now it warms me up. That's exactly the wrong way to think about this. With this logic, you need to think not emotionally, but you need to think about physiologically. Negative feedback, you reverse the stimulus. Positive feedback, you amplify the stimulus. Okay. Gang, do you have any questions? Okay, great, good job. I think we're done with chapter 1. Okay. All right. So I'm going to shift gears to chapter 2 at this time. Okay. So chapter 2. Chapter 2 is the chemical level of organization. This is the obligatory chemistry chapter you have in basically every biology course. You will not be a chemistry expert by taking this course and doing this chapter, right? You need a full year, multiple years of really chemistry training to become a chemist. But nonetheless, it is true that the biology of our body functions based on chemical principles. So this is just an attempt to start having a conversation about chemistry in the body. Okay, so chapter 2. Here we go. Okay, so let's see what we can start with here. Okay. I think what I will start with is atomic structure. Okay, atomic structure is covered basically on page 31 of the textbook. Somewhere around table 2.1 and figure 2.1 is information on the structure of atoms. Okay. All right. So we know, and I'm sure you know this, I mean, you know, if you were raised in the United States and you've been through the traditional high school sequence, certainly the word atom has come across your plate. So this shouldn't be a surprise. But let's talk about this. First off, let's define what atoms are. Okay, atoms are the building block of matter. Okay, I like to think of them as the Lego bricks of the universe, right? Anything that you might put your hand on and hold up, a pen, some writing pad here, your textbook, touch your hair, touch your skin. This is all atoms, right? The air in the room is made of atoms that are in gas form. You're inhaling them into your lungs. They're going into the alveolar sacs of your lungs, crossing the respiratory membrane, diffusing into the bloodstream, binding to hemoglobin, all that kind of good stuff, right? Atoms are the basic building blocks of matter in the universe. Okay, they are the Lego bricks of matter. All right. All atoms have a nucleus. The nucleus contains the subatomic particles, protons and neutrons. You see this in figure 2.1. Okay. We can talk about protons, neutrons, and electrons. A proton is a subatomic particle, right? It is smaller than an atom, and it is defined to have a positive charge. A neutron is a subatomic particle. It is defined to have no charge, to be neutral, okay? And then sitting outside the nucleus, but still part of the structure of the atom, would be the electrons. An electron is a subatomic particle that orbits outside the nucleus of the atom. And this subatomic particle is defined to have a negative charge. Okay, so what makes folks uncomfortable about this topic is that these are certainly things that we don't tend to think of on a daily basis. We just kind of take it for granted that the objects in our realm of influence behave in an expected way that we've come to know through living life for 18 or so years. We don't really think about these things. Well, until there's some sort of problem, right? When the lights go off in our house, we're like, well, where the heck's the electricity, right? So then we think about these things. All right. So that's just the most primitive explanation or description of what atoms are. And again, you really would need to take a chemistry course to become expert at this. But there are some principles that we're going to want you to start getting comfortable with. And so I'm going to move over to page 32, somewhere around figure 2.2 in your textbook. Somewhere around figure 2.2 in your textbook. And we're going to take a look at some concepts that come up in the reading of your textbook around this page. And so some related concepts here. Okay. All right, so the first concept is that of atomic number. Okay, atomic number refers to the number of protons present in the nucleus of an atom. And this is a very important characteristic or feature of every type of atom that exists on the periodic table, because the atomic number gives scientists a way to distinguish one kind of element, one kind of atom from another kind of atom. Okay, so you might think of atomic number as almost the fingerprint of an atom, because it allows you to identify the type of atom you're dealing with. So atomic number refers to the number of protons in the nucleus of an atom. Okay, and it's important that you appreciate the atomic number allows a human being, a scientist, to tell one kind of atom from another type of atom, allows you to distinguish different atoms. This property of atoms allows a scientist to distinguish different types of atoms. Okay, so I'm going to ask a question in the chat window. All right, take a look at figure 2.2. Take a look at figure 2.2 in your digital textbook. Here we go. What are the atomic numbers of iodine and carbon, respectively? What are the atomic numbers of iodine and carbon, respectively? Okay, great job. We're getting some responses very rapidly here. You see it is 53 for iodine and 6 for carbon. Nicely done. And gang, as you look at figure 2.2, as you look at each of the 8 different types of atoms that are present in that chart, in that figure, do you notice that every different type of atom does have a different atomic number? There are no 2 atoms in figure 2.2, and I dare say there are no 2 atoms on the periodic table of elements. You might remember from chemistry class in high school, there are no 2 elements that have the same atomic number. Every unique type of atom, every unique chemical element has a unique atomic number, and that's what we're trying to get across to you at this time. Okay. All right. Any questions so far? Okay. So, when you look at a picture like figure 2.2, don't bother trying to memorize these things. That's why we have that's why we have books and charts and tables and computers to look stuff like this up, but be aware of what an atomic number is, okay? All right, let's continue here. So on figure 2.2, there's two other properties or characteristics of the atoms that are listed. We have mass number and atomic number. So, if you look carefully at mass number and atomic number, they're often very close to being the same, but not quite, right? For example, the mass number of hydrogen is 1 or 2, and the atomic mass of hydrogen is 1.01. The mass number of carbon is 12 or 3, and the atomic mass of carbon is 12.01. So what I'm trying to suggest to you is that there is some relatedness between the concepts of mass number and atomic mass. Even though they're not exactly the same thing, there is a relationship. So let's talk about this in your notes. Okay, so atomic mass. Let's take atomic mass first. Okay, I'm going to put a statement in your notes at this time. And I'm going to put a fill in the blank line, and I want you to look at the sentence on your computer and see if you can give me the missing word. See if you can give me the missing word. Here we go. Atomic mass refers to the blank number of protons plus neutrons present in a group of atoms. Atomic mass refers to the blank number of protons plus neutrons present in a group of atoms. What is that word that should be in the blank space?
Total?
Not total, not weight, not sum. Okay, but all right, so let me point you to this. I want everybody to look at the chat window and look at all the responses that have been given so far. One of your classmates has the correct answer. Which answer do you think is correct? Okay, all right, yes, okay, good. Now you're starting to get at it. It's the average. That's right, average. Okay, so the correct response here is average. Okay. Atomic mass refers to the average number of protons plus neutrons present in a group of atoms. When I say a group of atoms, I'm talking about a group of the same kind of atoms. So if you had 10 atoms, they would all be carbon, or 10 atoms that were all nitrogen, or 10 atoms that were all hydrogen. A group of atoms that are the same type of atom, okay? That's atomic mass, okay? So you might say to yourself, well, if you look at, the atomic masses reported in figure 2.2, you notice that the numbers are not whole numbers. They're not integers. They're real numbers because there's a decimal point there, right? For example, the atomic mass of carbon is 12.01. The atomic mass of potassium is 39.10. Atomic mass of iodine is 126.90. Okay, so it's kind of like this, folks. You might have seen or heard a statement from the United States government, and the government might say the average American family has 4.2 children or 4.5 children. And you might say, well, heck, how can you have a half a child? Well, please realize that every individual family does not have a half a child. But if you have one family that has a size of 3 and another family that has a size of 4, then the average of 3 plus 4 is 3 plus 4 equals 7 divided by 2 equals 3.5, right? So while each individual atom will not have a fractional number of protons plus neutrons, if you count up the protons and neutrons in different atoms and you average them, you can get a fractional answer. Okay, so let me ask this in the chat window. Are you okay right now? Is this making sense? Would you like to ask anything? Okay, all right. Without questions, I will assume that you're okay. So yes, atomic mass is the average number of protons plus neutrons present in a group of atoms that are the same type of atom. Okay. There is a related idea of mass number. Okay. Mass number. And by the way, I need to say this since I'm old. Okay. Since I'm old, I need to tell you this. Atomic mass used to be referred to as atomic weight. Okay. So historically, this was called atomic weight. Atomic weight is not really a proper phrase anymore. It's been deprecated, but I'm telling you this because in some books you might still see the phrase atomic weight, and because your teacher's old and I was taught atomic weight, not atomic mass. Sometimes I slip back into that thinking, okay? So atomic weight is the old version of what today is atomic mass. Technically, atomic weight is not correct anymore. Okay. So mass number refers to the number of protons and neutrons present in a single individual atom, period. Okay, because this is reporting the number of protons plus neutrons present in a single individual atom. You're never going to have an average because it's kind of like having a family that has 2 boys and 3 girls, so it's 5, or a family with 4 boys and 1 girl, so it's 5 again, right? You're never going to have a fraction with one family. You're never going to have a fraction with one atom. Okay. All right, so atomic mass refers to a group of atoms. That's why it's an average. Mass number refers to a single individual atom, which is why these numbers reported for mass number are always integers. They're always whole numbers. Okay. Now let me say something here. You notice that the mass number for oxygen can be 16, 17, or 18. So now wait a second. Okay, if these are all oxygen atoms, how in the world can I have 16 or 17 or 18? So here's my question to you. Okay, here's my question to you, and I'll put it in the notes. What concept is being foreshadowed by the observation that carbon can have 3 different mass numbers? Okay. All right. What concept is being foreshadowed here? And Jared, thanks for responding. How about the rest of you? Okay. So if you don't know, well, take a look at the chat window and you'll see some answers that are correct. And I'm talking about the idea of isotopes, right? Isotopes, an isotope is the concept that's being foreshadowed here, being pointed out, being hinted at, being suggested, okay? So let's talk about isotopes just briefly. Isotopes refer to different versions of the same type of atom. That would be kind of a generic definition, okay? Isotopes refer to different versions of the same type of atom. Different versions of the same type of atom. Think of it like the phrase ice cream. Ice cream is ice cream, but I could be referring to different flavors of ice cream, different versions of ice cream. I could be talking about chocolate ice cream, strawberry ice cream, mint chocolate chip, banana ice cream, whatever you like, different flavors of ice cream, different versions of ice cream, different versions of the same type of atom. Isotopes are different versions of the same type of atom. From a formal perspective, isotopes refer to atoms that have the same atomic number, so therefore they have the same number of protons, but they have different numbers of neutrons present in the nucleus. Okay. All right. So I have a question for you. I'm going to put into the chat window. Okay. And put it into the chat window here. Hold on a sec. Take me a moment. Here it comes. Okay. How many neutrons are present in an oxygen atom with a mass number equal to 17? Okay. All right. Okay, so we're getting a lot of correct answers here, and that's very encouraging. Okay. So Lauren Umble. Lauren, could you unmute your microphone for a second? Are you with me, Lauren?
Yeah.
Hi, Lauren.
Hi.
Lauren, can you tell everybody how you came to the answer of 9 for this question?
I don't know. I'm confused.
So don't be nervous. Just think about, what process did you go through in your mind to come to the number of 9?
Say that again? It cut out for a second.
Sure. So let me repeat the question to Lauren. I'm asking Lauren to explain how you calculated the number of 9 for the question that was put in the chat window. Lauren, do you want me to skip you right now?
Yeah, can you come back to me?
Okay, fair enough. Anybody else want to take a, oh, okay, I see Brendan's hand up. Go ahead, Brendan.
So first off, it's an oxygen. So oxygen has 8 protons just because it is oxygen. So from there, we take 17 minus 8. Whatever remains has to be the number of neutrons if we're not counting like the point something that would be electrons in most cases.
Correct, Brendan. Nicely done. And so I want to be sure that everybody gets that. So I'll type this into the notes and then we'll finish for today, okay? So, question. how many neutrons are present in a carbon atom with a mass number equal to 17? The answer is 9, right? So 17 is going to be your number of protons plus neutrons. That's the mass number. Okay. The atomic number is 8. That's the number of protons. So doesn't it make sense if we take 17 and subtract 8 from it? We're going to end up with 9 neutrons. Okay. Yes, I do mean oxygen. Thank you for correcting me there. Yep. Absolutely. How many neutrons are present in an oxygen atom with a mass number equal to 17? So 17 minus 8 gives you 9. Okay, folks. This is probably a good stopping point, so we'll rest at this point. And let's see here. Time is about 9:17 by my watch. So let's break till 9:32. The Zoom channel will stay on, stay open. Please come back at 9:32. We'll get lab started for today. Okay. See you in about 15.